Welcome back. We're almost to the end of the course. Congratulations on making it all the way here. I hope you're starting to see just how practical these lessons are in a real-world IT environment, and that you're feeling empowered by your new troubleshooting skills. In past modules, you've learned how to troubleshoot and debug a bunch of situations. We saw how reducing scope and isolating problems can lead us to the root cause of programs that are running slowly or crashing unexpectedly. We also learned how to understand different error messages and use the tools available in the OS to diagnose what's going on. In the next few videos, we'll explore how we can figure out what's going on with programs that exhaust resources on our computer, whether that's memory, disk, or even network link. Then we'll talk about managing our most valuable resource of all, time. We'll learn how we can look at the never-ending list of tasks that needs to be done and make sure that we're spending our time wisely by prioritizing our work and avoiding unnecessary interruptions. After that, we'll discuss how we can apply all our new knowledge to try to avoid future problems. Being proactive can help us mitigate issues when things don't go according to plan. Hint, they rarely do. And even avoid problems altogether by catching them in the test infrastructure. And finally, you'll have another opportunity to try your hand at solving a real-world challenge to put your skills into practice. Ready to get started? All right, let's do it. Most applications need to store data in memory to run successfully. We called out earlier how processes interact with the OS to request chunks of memory and then release them when they're no longer needed. When writing programs in languages like C or C++, the programmer is in charge of deciding how much memory to request and when to give it back. Since we're human, we might sometimes forget to free memory that isn't in use anymore. This is what we call a memory leak. A memory leak happens when a chunk of memory that's no longer needed is not released. If the memory leak is small, we might not even notice it, and it probably won't cause any problems. But when the memory that's leaked becomes larger and larger over time, it can cause the whole system to start misbehaving. Not cool, memory leak. Not cool. When a program uses a lot of RAM, other programs will need to be swapped out, and everything will run slowly. If the program uses all of the available memory, then no processes will be able to request more memory, and things will start failing in weird ways. When this happens, the OS might terminate processes to free up some of the memory, causing unrelated programs to crash. You might be thinking, why should I care if I don't plan to code in C or C++? It's true that languages like Python, Java, or Go manage memory for us. But things can still go wrong if we don't use the memory correctly. To understand how this works, let's look into what these languages do. First, they request the necessary memory when we create variables. And then they run a tool called garbage collector that's in charge of freeing the memory that's no longer in use. To detect when that's the case, the garbage collector looks at the variables in use and the memory assigned to them, and then checks if there are any portions of the memory that aren't being referenced by any variables. Say, for example, you create a dictionary inside a function. Use it to process a text file, calculate the frequency of the words in the file, and then return the word that was used the most frequently. When the function returns, the dictionary is not referenced anymore, so the garbage collector can detect this and give back the unused memory. But if the function returns the whole dictionary, then it's still in use, and the memory won't be given back until that stops being the case. When our code keeps variables pointing to the data in memory, like a variable in the code itself or an element in a list or a dictionary, the garbage collector won't release that memory. In other words, even when the language takes care of requesting and releasing the memory for us, we could still see the same effects of a memory leak. And if that memory keeps growing, the code could cause the computer to run out of memory just like a memory leak would. The OS will normally release any memory assigned to a process once the process finishes, so memory leaks are less of an issue for programs that are short-lived, but can become especially problematic for processes that keep running in the background. Even worse than these are memory leaks caused by a device driver or the OS itself. In these cases, only a full restart of the system releases the memory. Say you notice that your computer seems to run out of memory a lot. You look at the running programs over the course of some time and realize that there's a process that keeps using more and more memory as the hours pass. If you restart that process, it begins with a very small amount of memory, but quickly requires more and more. If that's the case, it's pretty likely that this program has a memory leak. So let's jog its memory. What can we do if we suspect a program has a memory leak? We can use a memory profiler to figure out how the memory is being used. As with debuggers, we'll have to use the right profiler for the language of the application. For profiling C and C++ programs, we'll use Valgrind, which we mentioned in an earlier video. For profiling in Python, there are a bunch of different tools at our disposal, depending on what exactly we want to profile. We can be as detailed as profiling the memory usage of a single function, or as big picture as monitoring the total memory consumption over time. Using profilers, we can see what structures are using the most memory at one point in time, or take snapshots at different points in time and compare them. The goal of these tools is to help us identify which information we're keeping in memory that we don't actually need. It's important that we measure the use of memory first, before we try to change anything. Otherwise, we might be optimizing the wrong piece of code. Sometimes, we need to keep data in memory, and that's fine. But you want to make sure that you're only keeping the data that you actually need, and that you let go of anything you won't be using. That way, the garbage collector can give that memory back to the OS. And of course, if you check that you're using the memory correctly, but still find that you're exhausting available RAM, it might be time for an upgrade. Did you commit all that to memory? Don't forget, there's a lot more to say about memory profiling than we have time to cover. But we've included links to more information about some of these profiling tools in the next reading. Up next, we'll talk about a different resource that might need some special care: disk space. Another resource that might need our attention is the disk usage of our computer. Programs may need disk space for lots of different reasons: installed binaries and libraries, data stored by the applications, cached information, logs, temporary files, or even backups. If our computer is running out of space, it's possible that we're trying to store too much data in too little space. Maybe we have too many applications installed, or we're trying to store too many large files on the drive. But it's also possible that programs are misusing the space allotted to them, like by keeping temporary files or caching information that doesn't get cleaned up quickly enough, or at all. It's common for the overall performance of the system to decrease as the available disk space gets smaller. Data starts getting fragmented across the disk, and operations become slower. And when a hard drive is full, programs may suddenly crash while trying to write something to disk and finding out that they can't. A full hard drive might even lead to data loss, as some programs might truncate a file before writing an updated version of it, and then fail to write the new content, losing all the data that was stored in it before. Yikes. If it gets to this point, we'll probably see some error like no space left on device when running our applications or in the logs. So what do you do if a computer runs out of disk space? If it's a user machine, it might be easily fixed by uninstalling applications that aren't used or cleaning up old data that isn't needed anymore. But if it's a server, you might need to look more closely at what's going on. Is the issue that you need to add an extra drive to the server to have more available space? Or is it that some application is misbehaving and filling the disk with useless data? To figure this out, you'll want to look at how the space is being used and what directories are taking up the most space. Then, drill down until you find out whether large chunks of space are taken by valid information or by files that should be purged. For example, on a database server, it's expected that the bulk of the disk space is going to be used by the data stored in the database. On a mail server, it's going to be the mailboxes of the users of that service. But if you find that most of the data is stored in logs or in temporary files, something has gone wrong. One common pattern of misbehavior is a program that keeps logging error messages to the system log over and over. This can happen for lots of different reasons. For example, the OS might keep trying to start a program that fails because of a configuration problem. This will generate a new log entry with every retry and can take up a lot of space if there are several retries per second. Or it could be that the server has a lot of activity and the logs are real, but there are just too many of them. In that case, you might want to look into tweaking the configuration of the tools that rotate the logs more frequently to make sure that you're keeping only what you need. In other cases, the disk might get full due to a program generating large temporary files, and then failing to clean those up. For example, an application might clean up temporary files when shutting down cleanly, but leave them behind if it crashes. Or it could simply be a programming error of creating temporary files and never cleaning them up. In a case like this, you'll ideally have some housekeeping to fix the program and delete those files correctly. But if that's not possible, you might need to write your own script that gets rid of them. A situation that might be tricky to debug is when the files taking up the space are deleted files. I'm sure you're wondering, how can deleted files take up space? Great question. Well, if a program opens a file, the OS lets that program read and write from the file regardless of whether the file is marked as deleted or not. So, lots of programs delete the temporary files they create right after opening to avoid issues with failing to clean them up later. That way, the process can read from and write to the file while the file is open, and then when the process finishes, the file gets closed and actually deleted. Now, this system is widely used and works fine for most processes. But if for some reason this temporarily deleted file starts becoming super large, it can end up taking up all the available disk space. If that happens, we'll be left scratching our heads when trying to figure out where most of the data went, since we won't see these deleted files. To check for this specific condition, we need to list the currently open files and comb for the ones that we know are deleted. We'll include pointers to the commands for how that works in the next reading. Of course, there are all kinds of other reasons why the disk may be getting too full. Just remember that whenever this happens, your process will remain the same. You'll need to spend some time looking into what's using the disk. Check to see if it's expected or an anomaly, figure out how to solve it, and most important of all, how to prevent it from happening again. Up next, we'll discuss yet another resource that might cause some trouble: the network. When you work in IT, you interact with services all over the internet. At one moment, you might connect to a service running on your local network, and the next, use another service running in a data center located on a different continent. If your network connection is good, you might not be able to tell the difference where the website you're browsing is hosted. But if you're dealing with a networked service that isn't exactly up to speed, you might need to get more details about the connection you're using. The two most important factors that determine the time it takes to get the data over the network are the latency and the bandwidth of the connection. The latency is the delay between sending a byte of data from one point and receiving it on the other. This value is directly affected by the physical distance between the 2 points and how many intermediate devices there are between them. The bandwidth is how much data can be sent or received in a second. This is effectively the data capacity of the connection. Internet connections are usually sold by the amount of bandwidth the customer will see. But it's important to note that the usable bandwidth to transmit data to and from a network service will be determined by the available bandwidth at each endpoint and every hop between them. To understand how latency and bandwidth interact, think about what happens when you try to visit a website over the internet. If the web server is hosted somewhere across the ocean, the latency might be 100 milliseconds or so. That's the time it takes for your request to reach the server. The server will then generate a response and send it back to you. The first bytes of the response will again take 100 milliseconds to zap across the pond to your computer. Once the response is on its way, The time it takes for the rest of the data to arrive is determined by the bandwidth. If the available bandwidth between the 2 points is 10 megabits per second, you'll be able to receive 1.25 megabytes every second. So, for a website of about 1 megabyte of content, that large initial latency will be noticeable, since it's an extra 20% on top of the total time to download it. But if the content is 10 megabytes or more, the initial latency will be less than 5% of the total time to download it, so it matters less. Let's say you're trying to figure out why a network connection isn't going as fast as you want. Remember that if you're transmitting a lot of small pieces of data, you care more about latency than bandwidth. In this case, you'll want to make sure that the server is as close as possible to the users of the service, aiming for a latency of less than 50 milliseconds if possible, and up to 100 milliseconds in the worst case. On the flip side, if you're transmitting large chunks of data, you care more about the bandwidth than the latency. In this case, you'll want to have as much bandwidth available as possible, regardless of where the server is hosted. What do we mean by bandwidth available? Computers can transmit data to and from many different points of the internet at the same time, but all those separate connections share the same bandwidth. Each connection will get a portion of the bandwidth, but the split isn't necessarily even. If one connection is transmitting a lot of data, there may be no bandwidth left for the other connections. When these traffic jams happen, the latency can increase a lot because packets might get held back until there's enough bandwidth to send them. You've probably experienced this already on your own computer. If you've ever run several applications using the same network at once, the overall connection speed may have seemed slower. You can check out which processes are using the network connection by running a program like if.top. This shows how much data each active connection is sending over the network. You might also have noticed that the more users sharing the same network, the slower the data comes in. This is true for home connections and office connections alike. No matter how much bandwidth you have, it's a limited resource, so you'll need to be careful with how you share it among its users. If some applications are using so much bandwidth that others can't transmit any more data, it's possible to restrict how much each connection takes by using traffic shaping. This is a way of marking the data packets sent over the network with different priorities to avoid having huge chunks of data use all the bandwidth. By prioritizing accordingly, processes that send and receive small packets can keep working fine, while processes that need the most bandwidth can use the rest. There's also a limit to how many network connections can be established on a single computer. This isn't usually a problem, but there could be bugs in the software that causes it to open way too many connections, or keep old connections open even if they're no longer in use. If this happens on a server, no new users will be able to connect to it until whatever's keeping those connections open closes them. Up next, we'll try our hand at solving another real-world example. This time, we'll be dealing with a memory leak and adjusting our program to make better use of our resources. There's a ton of reasons why an application may request a lot of memory. Sometimes, it's what we need for the program to complete its task. Sometimes, it's caused by a part of the software misbehaving. First, let's trigger the misbehavior ourselves to see what this looks like. We'll use a terminal called UX_term for that. We've configured this terminal to have a really long scroll buffer. The scroll buffer is that nifty feature that lets us scroll up and see the things that we executed and their output. The contents of the buffer are kept in memory. So if we make it really long and we manage to fill it, we'll cause our computer to run out of memory. With normal use, it might take ages until that happens. But if we run a command that keeps generating a lot of output, we could manage to fill that buffer pretty quickly. Say we ran a command like od-cx-dev-urandom. This command will take the random numbers generated by the urandom device and show them as both characters and hexadecimal numbers. And Since the urandom device keeps giving more and more random numbers, it will just keep going. Our command is filling up the scroll buffer, making our computer require more and more memory. In a different terminal, let's open Top and check out what's going on. Pressing Shift-M, we tell Top that we want to order the programs by how much memory they are using. We see that the percentage of memory used by Xterm is going up super quickly. Let's stop the process that's filling up the buffer by pressing Ctrl-C. With that, we stop the command that was filling the buffer, but the terminal still has that memory allocated, storing all the lines in the scroll buffer. Let's look at the output of Top in a bit more detail. There's a bunch of different columns with data about each process. The column labeled RES is the dynamic memory that's preserved for the specific process. The one labeled SHR is for memory that's shared across processes. And the one labeled VIRT lists all the virtual memory allocated for each process. This includes process-specific memory, shared memory, and other shared resources that are stored on disk, but mapped into the memory of the process. It's usually fine for a process to have a high value in the VIRT column. The one that usually indicates a problem is the RES column. All right, let's close the other terminal so that it releases all the memory that it reserved. In this example, we saw what a program that keeps requesting more and more memory looks like. This was a super extreme example. Most memory leaks don't happen at this speed. It can usually take a long while until we notice that a program is taking more memory than it should. And it might be hard to tell the difference between memory that's actually needed and memory that's being wasted. But looking at the output of Top and comparing it to what it used to be a while back is usually how any investigation into a memory leak starts. Let's look at a different example. We have a script that analyzes the frequency of words in web pages. This script works fine when it's just a few web pages, but if we try to give it all the Wikipedia contents, it starts using up all the memory. Let's run it first and see what happens. Okay, this is running, and it will take a long while to finish. It's processing a huge amount of articles after all. While this is running, let's look at the output of Top in a different terminal and see what we find. We see that there's a bunch of different content stats processes running. That's because our script is using the multiprocessing techniques that we saw in an earlier video to parallelize the processing of the information and get the results as fast as possible. It seems like these scripts are taking a lot of memory, so let's sort it out to see the details. Whoa! We see that the memory used by one of the processes in particular keeps growing and growing. The application is processing a bunch of data and generating a dictionary with it, so it's expected that it will use some memory, but not this much. This looks like the program is storing more than it should in memory. This program is pretty complex, so we could use the help of a memory profiler here to figure out what the problem is. Let's stop it now and use a profiler to figure out where our computer's memory is going. To do that, we'll need to use a simplified version of our code, as profiling the memory of a multi-process application is extra hard. And instead of processing all the articles, we'll just handle a few, so that we can check out the memory consumption quickly. Let's open our simplified script and have a look. We'll be using a module called Memory Profiler. This is one of the many different memory profilers available for Python. We've added this @profile label before the main function definition to tell the profiler that we want it to analyze the memory consumption of it. This type of label is called a decorator, and it's used in Python to add extra behavior to functions without having to modify the code. In this case, the extra behavior is measuring the use of memory. The rest of the code is basically the same as the original one. It just uses a single process and is limited to 50 articles instead of the thousands of articles that the other script was going through. We're running the script with the memory profiler enabled. This is just reading through 50 articles, but it takes a bunch of time because all that memory profiling makes our script slower. Once the program finishes, the memory profiler gives us information about which lines are adding or removing data from the memory used by the program. The first column shows us the amount of memory required when each line gets executed. The second one shows the increase in memory for each specific line. We see here that after going through 50 articles, the program already took 130 megabytes. No wonder we ran out of memory when we were trying to process all the articles. We can see that the variables that require the most memory are article and text, with about 4 and 3 megabytes respectively. Those are the articles we're processing, and it's fine for them to take space while we're counting the words in the article. But once we're done processing one article, we shouldn't keep that memory around. Can you spot the problem? Right at the end, the code is storing the article to keep a reference to it, but it's storing the whole article. If we want to keep a reference to all the articles that include a word, we could store the titles or the index entries, definitely not the whole contents. From updated calendars to social media detoxes, there's lots of different ways to optimize our time. One that's super effective when working in IT is the Eisenhower decision matrix. When using this method, we split tasks into two different categories: urgent and important. There are tasks that are important and urgent. Draw alarm bells around them if you'd like, because these need to be done right away. For example, if the company's internet connection is down, it's both urgent and important to get it back up as soon as possible. Some tasks are important, but not urgent, so they need to get done at some point, even if it takes a while to complete them. For example, as a follow-up to the network being down, it would be important to make sure that there's a backup network connection so that if the existing one is ever down again, the company can stay connected using the backup. Other tasks might seem urgent, but aren't really important. A lot of the interruptions that we need to deal with are in this category. Answering email, phone calls, texts, or instant messages feel like something that we need to do right away, but most of the time are not really the best use of our time. And finally, there's a whole category of tasks that are neither important nor urgent. These are distractions and time wasters that shouldn't be done at all. These include meetings where nothing useful is being discussed, email threads that lead to nowhere, office gossip, no thanks, and any other tasks that eat up our time without giving anything valuable in return. In general, to make the most of our time, we need to make sure that we're spending the majority of it on tasks that are important. Of course, we'll want to get to the urgent tasks as soon as possible, but we need to block some time for long-term planning and execution. Spending time on long-term tasks might not bear fruit right away, but it can be critical when dealing with a large incident. For example, setting up your infrastructure so that you can easily roll back changes or deploy new servers when needed takes a large chunk of time. But investing in the future can save you even more time and user frustration when responding to a problem. Researching new technologies is another task in this category. IT is always evolving, and it's important to have time set aside to stay up to date. Figure out if it's time to migrate the web server to different software, update the mail server to a new OS version, or deploy voice over IP throughout your company. Another important task that might not necessarily be urgent is solving technical debt. When you work in IT, you hear this term a lot. What does it mean? Technical debt is the pending work that accumulates when we choose a quick and easy solution instead of applying a sustainable long-term one. We called out a few times already that when solving a problem, we might apply a short-term remediation to fix it right away, and then plan for a long-term solution to prevent it from happening in the future. Until we have a fix that sticks, the workaround we created is technical debt because we need to spend time keeping it in place, even if it's not the best solution. Whenever we go for a short-term solution and leave the long-term solution for later, we're creating technical debt. This might be the right decision in the moment to get us out of a crisis and let our users get back to work. But we need to then schedule time to apply the long-term solution that will make our future lives easier. Technical debt can also be generated by external parties. For example, when a new version of the software we're using is released, we'll need to schedule time to upgrade it. And until we do, that pending upgrade is technical debt. Okay, so we've made it clear that we need to focus our work on tasks that are important. But what can we do about interruptions, which are urgent but not important? If you work in IT support, you'll have to be interrupted. It's part of the role. So you'll need to plan to deal with those interruptions effectively. If you work on a team, you can rotate the person dealing with those interruptions. Maybe someone takes care of them in the morning and a different person in the afternoon. Or you take turns each day. If you work independently, you can try to establish a set of hours when users can expect to reach you for normal requests, and the rest of the time only be available for emergencies. The key here is to have a window of time reserved when you're not going to be interrupted. That's the time when you can get the most important tasks done, when you can fully concentrate on dealing with complex issues and finding solutions for tricky problems. Depending on your role and how the company works, you might need to get this work done in a different location to avoid people walking up to your desk. Or actively silencing any of your notifications to avoid getting interrupted and distracted by unimportant conversations. Okay, so assuming that you've managed to set some time aside to work on these important but not urgent tasks, how do you make sure that you work on the right things with the right priorities? That's coming up in our next video. Say you need to deploy a new computer for the person that's starting tomorrow. Upgrade the VPN service to the latest version because the old one has a security vulnerability. Fix a permissions problem that's preventing a group of users from accessing the inventory data. Check out a problem with the mail system that's causing some emails to get randomly rejected. And so many other things that by now you've lost track of them. What can you do to figure out how to spend the limited time that you have? There's a lot to say about this, and everyone works a little differently, so you'll need to find the system that works best for you. But let's cover the basic structure that can help us get organized and prioritize our tasks. The first step is to make a list of all of the tasks that need to get done. You can make this list on a piece of paper, a text file on your computer, a bug tracking system, or a ticket management system. Whatever works for you. The point is to have all the tasks listed in one place to avoid depending on your not always perfect memory later. Once you have the list, you can check the real urgency of the tasks. Ask yourself, if any items don't get done today, will something bad happen? If yes, then those should be worked on first. Once you're done with the most critically urgent tasks, you can look at the rest of the list and assess the importance of each issue. Even when it looks like everything is important, you should be able to tell that some things are more important than others. For example, a task that will benefit more people is more important than a task that will benefit less people. If there are a bunch of different tasks that depend on you completing one, that roadblock is more important to clear than the rest. If it still seems like everything is on fire, you can try dividing the tasks into groups of most important, important, and not so important, and then sort the tasks inside each group. But don't spend too much time doing this sorting. In the end, the exact order isn't what matters. What matters is that you spend most of your time working on the most important tasks. And if you work with a team of people, it's a good idea to share both the lists of tasks and the standard of prioritization among team members. This helps you avoid having to do the work multiple times and coming out with different priorities. Once you have a list of the most important tasks to work on, you'll want to have a rough idea of how much effort they'll take. We'll talk more about estimating times in the next video. This isn't about exact timing. It's about assigning rough sizes. One common technique is to use small, medium, and large. And when the range of sizes is big enough, include extra small or extra large if needed. Once you identify the most important tasks and how big they are, you can start working on them. If possible, try to start with the larger, most important tasks to get those out of the way first. But as we called out, when our work involves IT support, we know that we'll have to deal with interruptions. And working on complex tasks while getting interrupted can be very frustrating. I hear that. One strategy that can help us with that is saving the most complex tasks for the moments when we're less likely to get interrupted. If you know that you get busiest in the morning and you tend to have more quiet time during the afternoon, it makes sense to work on easy and quick tasks early in the day. Save the most complex tasks for later, when you'll have more time to concentrate on them. But when your focus time starts, you should make sure that you work on those large, complex tasks and not on the easy ones. Otherwise, the complex tasks will never get done. The key here is to always work on important tasks. If a task is not important, it shouldn't be done at all. Really, we live by this rule here at Google. Then select which task you're going to deal with depending on urgency and how much time you can devote to it, starting with the biggest tasks that you can fit in the time you have available. But keep in mind, this shouldn't stop you from taking a break or working on experimental projects. Taking breaks is important because it allows our creative minds to stay fresh. And working on a fun side project can help us research emerging technologies and come up with new ideas. Did you know that this very certificate program got its start as a side project at Google? Okay, but what if the unthinkable happens? What can we do if after all of this prioritizing, sizing, and ordering, there's just too much work to be done and too few hours in the day? The first thing to know is this is normal. Most people working in IT have too much to do and can't get all the things they want done. Unfortunately, us humans can't multiply ourselves on command yet. And working extra hours is not sustainable long term, which means there are basically two options. Either you get extra help from other team members, or you decide that some tasks weren't really that important and they won't get done. For both of these options, you'll need to involve other people, like your manager, and make sure that expectations get clearly communicated. Some tasks, like fixing the permissions in a directory, changing a faulty keyboard, or installing a new application on a single computer, can be self-contained and completed in a small amount of time. Other tasks, like upgrading the database software to a new version, automating the creation of user accounts, or writing a wrapper to adapt two incompatible programs, are larger projects that can take several days or maybe even weeks to complete. When that's the case, it's important to have a rough estimate of how long the tasks will take to be completed and to clearly communicate expectations to those affected. As we've called out before, when deciding whether a manual task needs to be automated, we should consider two things: how many times we'll do the task over a period of time, and how long it takes to do it manually. From there, we can figure out if that number is larger than the time it will take us to write the automation. This sounds great in theory, but the problem is that we don't know how long it'll take us to write the automation until we've actually written it. All we can do is estimate it, and most of us are really bad at estimating how long tasks will take. We tend to be too optimistic about the amount of time that a certain piece of code will take us to write, or a certain infrastructure will take us to set up. Usually, our first instinct is to consider how much we can get done with an ideal amount of focus on the work and a full grasp of the problem we're trying to solve. We forget to take into account the many obstacles that we might face, like finding a bug that we don't know how to fix, being interrupted by a problem that needs more urgent attention, or discovering that a new tool doesn't work well with the rest of the tools we have in place. So if you're trying to estimate how long it will take you to complete a project, big or small, you need to be realistic. Avoid being overly optimistic with your time estimates. The best way to do this is to compare the task that you're trying to do with similar tasks that you've done before. This way, you're not estimating based on how long you would like the project to take, but on how long other similar projects actually took in the past. If the task at hand is large, it might be hard to find something similar enough to use for comparison. So to make a better estimate of a bigger than average project, you'll want to chop it up. Split the task into smaller steps. Compare each step to a similar task that you've done in the past, and assign an estimated amount of time to each step based on that. If one smaller step is still too large, then split it into even smaller pieces until you can compare each piece of the puzzle with something that you've done before. Once you've got all those estimated times, just add them up, and you'll have a rough estimate of how long the whole task will take. But even that's going to be optimistic, since putting all the pieces together will take additional time. So once you have a rough estimate of the total time of all the steps, you'll want to factor in some extra time for integration. This should also come from prior experience. Think about how long it took you to integrate the pieces of a project before, and you'll have a rough idea of how much to add to the previous value. Time really flies, huh? Knowing how optimistic we humans are, even after basing those estimations on previous experience, the number you come up with is going to be very close to the best possible scenario. Even if you're prepared for something to go wrong, it's impossible to anticipate new, unknown bumps in the road. So take this estimation and multiply it by a factor. Once again, this factor works best when it's based on previous experience. So if the last time you did this exercise, it took you 3 times longer to complete the task than you had planned, go ahead and multiply your estimation by 3. This might seem like we're inflating the numbers, but remember, you want to have a grounded estimate of how long it will take you to complete the task. That means taking into account the obstacles that you'll certainly run into but haven't come across yet. No matter how detailed we are, the final estimation won't ever exactly match the time it takes. But it will give us a rough idea of whether we can complete the task in a few hours, days, weeks, or months. Once you've made your estimation, you'll want to note it down somewhere so that you can check later to see how close you were to the original number. You can adjust future estimations based on that. You'll also want to communicate with those affected and let them know when they can expect the task to be done. When you're dealing with an issue that's affecting one or more users, you might feel rushed to meet expectations set by the people you're helping. Everyone's got their own ideas of how long it will take you to solve the problem and when they can expect a solution. They might be wondering, what's the holdup? If the issue is that the user spilled coffee on their keyboard and needs a new one, the expectation is that replacing the keyboard will be a very small task that will take almost no time. If the issue is that there's a new employee starting soon and they need a new computer set up for them, the expectation is that it will take much longer than replacing a keyboard. Even if we have an automated process for setting up new computers, which means there's very little manual work. To have successful interactions with our users, it's important to understand these implicit expectations and let users know if fixing the problem will take longer than they expect. Users will be happy if the issue is resolved within their expectations, but will become frustrated if it takes much longer than they thought. But as long as we communicate with them early about the circumstances, they'll be able to understand this and manage their time accordingly. Say you have to replace a keyboard, but you have no spares available. This means you'll need to buy a new one, or maybe even a whole batch to have a spare available next time. It's important to communicate upfront to the user that, in this case, the replacements will take more time, and then figure out how critical getting the replacement is. If the user is an accountant working on the salary deposit order, which needs to be sent to the bank in 1 hour or nobody gets their payment on time, you might opt for giving them your keyboard while you go and buy another one at the closest hardware store. On the flip side, if the user can work on their laptop until the next day when a new batch of keyboards is scheduled to arrive, you don't need to go out of your way to get an early replacement. It's also important to let users know if there are any conflicting priorities that might delay the response to whatever they need. Say a user calls you to request access to a shared resource, but you're in the middle of dealing with an issue that's causing the company's database to be offline. Even if the user request is quick and easy to solve, fixing the database is critical and affects the whole company, so it should take priority. In this case, make sure you tell the user that you're dealing with a crisis and that you'll help with their request once the crisis is resolved. Give them an idea of when they can expect their issue to be fixed, so they can plan what to do next. So as a general rule, communication is key. Try to be clear and upfront about when you expect the issue will be resolved. And if for any reason the issue isn't solved by then, explain why and what the new expectation should be. Unfortunately, when the issue you're trying to solve involves troubleshooting and debugging, it's usually very hard to give an accurate estimate of how long it will take you to fix the problem. Notice a theme? Estimating the time it takes to perform more complicated work is tough. A lot of your time will be spent investigating, looking into what's going on, and figuring out what should be happening. In that case, make sure to let users know when they can expect an update on their issue, and give them timely updates. If possible, it's a really good idea to have users file their requests through a ticket tracking system. Using a system like this has a ton of advantages. Having all the work you need to do in one place lets you organize your tasks by priority, as we discussed before. Receiving reports of issues through a system instead of a phone or chat lets you make better use of your time. You can now decide when you'll look at the list of issues instead of getting interrupted in the middle of a task. And when you have an update for an issue that you've been working on, you can easily update the ticket with news, without having to track down users to let them know what's up with their requests. Finally, try out some practical shortcuts when dealing with users. It makes sense to take some time to think about the work you do and figure out ways to avoid interruptions and save time. For example, if a user tells you that their mouse doesn't work, your first instinct might be to go check it yourself, and then bring a new one if necessary. But that's a lot of back and forth. Instead, you could ask the user to bring the faulty mouse to you, so that you can test it at your computer, and if it's broken, change it with a new one. Or even better, if you trust your users, you might even leave a set of mice, keyboards, and other accessories available for users to take when the one they're using breaks down. That's what we do here at Google, and it saves us a ton of time and frustration. Along the same lines, if your company's budget allows, you could have a couple of spare computers ready to be used. That way, when a computer breaks down, you can get the user back to work as quickly as possible. Then you can debug the faulty computer at your own pace. But not every issue can be solved by having spare devices. Sometimes, spending time on improving your infrastructure can help you get more done in less time. Automating processes like installing new computers, setting up new user accounts, deploying virtual machines, or rolling back changes to previous versions can help save you a lot of time when you're responding to an incident. You might be wondering, why is debugging so hard that we need an entire course on it? Brian Kernighan, one of the first contributors to the Unix operating system and co-author of the famous C programming language book, among many other things, once said, "Everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it?" This is a warning against writing complicated programs. If the code is clear and simple, it will be much easier to debug than if it's clever but obscure. The same applies to IT systems. If the system is engineered very cleverly, it will be extremely hard to understand what's going on with it when something fails. It's important to focus on building systems and applications that are simple and easy to understand, so that when something goes wrong, we can figure out how to fix them quickly. So how do we do this? One piece of advice I found really valuable is to develop code in small, digestible chunks. Every so often, I stop and test what I've written. The hardest thing to do is to try to debug something if I'm running it for the first time only after I've completed it. There are so many places things could have gone wrong. Another lesson that's super useful is to keep your goal clear. If you're writing code, try writing the tests for the program before the actual code to help you keep focused on your goal. If you're building a system or deploying an application, having documentation that states what the end goal should be and the steps you took to get there can be really helpful to both keep you on track and figure out any problems that might turn up along the way. We called out at the beginning of this course that solving technical problems is a bit of an art, and that it can be fun when things finally click together. On the flip side, the worst part of troubleshooting and debugging is when we get stuck, when we can't think of any other reasons why the program is failing, or we can't figure out what else we can do to fix it. In this course, we've given you a bunch of tools and processes to follow that can hopefully help you avoid getting stuck on a lot of these situations. But we can't cover absolutely everything. You might still find yourself facing an issue that you have no idea what to do about. And that's okay. If you're in a sticky situation, the main thing to do is to remain calm. We need our creative skills to solve problems, and the worst enemy of creativity is anxiety. So if you feel that you're out of ideas, it's better to take your mind off the problem for a while. Maybe grab a cup of coffee, or take a walk outside. Sometimes a change of scenery is all we need for a new idea to pop up and help us figure out what we're missing. True in coding and in life. If the problem you're trying to solve is complex and affects a lot of people, it can get really stressful to try to fully debug it with everyone waiting on you. That's why it's better to focus first on the short-term solution and then look for the long-term remediation once those affected are able to get back to work. And don't be afraid to ask for help. Sometimes, just the act of explaining the problem to someone else can help us realize what we're missing. There's a technique called rubber duck debugging, which is simply explaining the problem to a rubber duck. It sounds whimsical, and you may look like a quack, but it can really work. Because when we force ourselves to explain a problem, we already start thinking about the issue differently. And remember that no one knows absolutely everything. Sometimes the best way to learn new skills and techniques is to ask others for help. We're all in this thing together. There are times when I know that if I spend enough hours on a problem, I'll probably figure out a solution. But is that the best use of my time? Usually, the better answer is to ask someone who has done it before, to save time and frustration. And then use the problem at hand as an opportunity to keep learning, so that the next time I can do it on my own. When you ask a colleague for their help with debugging a problem, be careful not to tell them what you think the root cause of the issue might be. Instead, tell them about the symptoms and see what questions they ask and what possibilities they probe. They might come up with completely different paths to explore. Of course, our lives as IT specialists would be much easier if we could avoid problems altogether. Up next, we'll look into some proactive approaches to catching issues before they affect any users. Something that IT specialists and exterminators have in common is dealing with bugs. I just love a good coding joke. Anyhow, moving on. It can be bugs in our software or someone else's software. But we'll come across lots of bugs that trigger lots of different failures in our programs. There's a bunch of strategies we can adopt to make our lives easier by catching issues before they affect our users, or making troubleshooting simpler by having better information. We've touched upon some of them here and there, but now it's time to deep dive. To avoid having to scramble to fix things when there's an outage, it's really helpful to have infrastructure that lets us test changes in advance, so that we can check that things are working as expected before they reach our users. If we're the ones writing the code, one thing we can do is to make sure that our code has good unit tests and integration tests. If our tests have good coverage of the code, we can rely on them to catch a wide array of bugs whenever there's a change that may break things. For these tests to be really meaningful, we need to run them often and make sure we know as soon as they fail. Setting up continuous integration can help with that. Another step in this direction is to have a test environment where we can deploy new code before shipping it to the rest of our users. This serves two purposes. First, we can do a thorough check of the software as it will be seen by the users. Depending on the software and how often we update it, we can do both automated and manual tests in this environment. And second, we can use this test environment to troubleshoot problems whenever they happen. We can try out possible solutions and new features without affecting the production environment. Taking this even further, another recommended practice when managing a fleet of computers is to deploy software in phases or canaries. What this means is that instead of upgrading all computers at the same time, and possibly breaking all of them at the same time, you upgrade some computers first and check how they behave. If everything goes fine, you can upgrade a few more, and so on until you're confident enough to upgrade the remaining part of the fleet. As the saying goes, like a canary in a coal mine. To make the best use of this practice, we'll need to be able to easily roll back to the previous version. Depending on the software, this might require more or less infrastructure. But trust me, it's worth spending the time setting up that additional infrastructure. If you deployed a software version that was broken and suddenly a bunch of your computers aren't working correctly, you'll want to roll them back to a previous state as fast as possible. Now, even with all these preventative measures, bugs will still filter through and problems will occur. We can make our troubleshooting easier by including good debug logging in the code. That way, whenever we have to figure out an issue, we can look at the logs and get a pretty good idea of what's going on. Another method that can help us is having centralized logs collection. This means there's a special server that gathers all the logs from all the servers, or even all the computers in the network. That way, when we have to look at those logs, we don't need to connect to each machine individually. We can comb through all the logs together in a centralized server. Similarly, having a good monitoring system can be super helpful. We can use it to catch issues early, before they affect too many users. And during a debugging session, we can look at the collected data to try to determine if there's anything out of the ordinary going on. We called out ticketing systems a few times already because we can't stress their importance enough. Making good use of them can help us save a lot of time when trying to get to the bottom of a problem. If we ask users to provide the needed information up front, we don't have to waste time and go back and forth. And even here, we can look at opportunities for automation. Say you almost always want some specific info from the user's computers. You can automate getting it by creating a script that gathers all the data you want and have the users attach it to the ticket. Finally, remember to spend time writing documentation. And just as importantly, store the documentation in a well-known location. Even if writing documentation isn't especially fun, having good instructions on how to solve a specific problem, knowing how to diagnose what's going on with a server, or tracking the known issues in a system can be real time savers. At Google, we have a bunch of docs called playbooks, where we detail what a person who's on call can do to diagnose and mitigate a ton of different problems. By keeping this information updated, we make sure that no matter who the person on call is, everybody has access to the knowledge base accumulated by the whole team. And it doesn't stop there. If we're dealing with systems that change and grow, we can proactively plan for the additional capacity that we'll need in the future. We discussed in earlier videos what we can do when our programs are misusing resources, like memory, disk, network, or CPU. But sometimes, it's not a question of misusing resources, but rather missing resources. A database server is expected to use more disk storage as more data gets stored. Or a web server is expected to use more network bandwidth as the service grows in popularity. If you're dealing with a service that's expected to grow and will require more resources in the future, it makes sense to spend some time thinking about what that might look like. Planning ahead will prepare you for when you need additional resources, instead of having to scramble for them at the last minute. Let's say the database growth is expected to be 1 megabyte per day, and you have 500 megabytes of free space. You can use that storage for almost 2 years. But if the growth is expected to be 10 megabytes per day, and you only have those 500 megabytes available, then you need to start figuring out a plan that will allow your database to keep growing at that pace. Otherwise, you'll run out of space in a couple of months. Once you've figured out the current usage and the expected growth, don't forget to write this down so you can refer to it in the future and check if anything has changed. If you find that you'll soon be running out of space, what you'll do next will depend on what the system does and the importance of the data. You might decide that you don't really want to store all that data, and instead, clean up anything that's not really necessary. Or you might decide that you really need to have a lot more storage available. In that case, you might opt for buying a network-attached storage, or NAS, that can be attached for your server for additional disk space. Migrating to a different type of storage takes time and can be tricky to do right under pressure, so it's important to do this kind of planning in advance and not wait until the disk is completely full. This means monitoring the usage growth of the computer to see if there are any trends that need attention. If the service using the database suddenly becomes very popular, the daily growth can increase so much that we'll need to find a better solution sooner than we thought. Our monitoring system should trigger an automatic alert when that's the case. An interesting strategy for making the best possible use of resources is to mix and match the processes that run on the computers so they make use of all the available resources. If you have a process that's CPU intensive and takes almost all the available CPU on a computer, you can still run processes that are I/O intensive, reading and writing a lot of data to the hard drive. Or if you have a service that requires a lot of RAM, you can pair it with another one that uses very little memory and mostly sends and receives data over the network. An alternative for having to deal with all these resources, like figuring out when to buy more and how to distribute them, is to migrate those systems to the cloud. Setting up your service to run in the cloud will require some initial setup time, as well as an ongoing cost for the cloud resources you're using. But while this is more expensive than what you'd pay when running the service on-premise, you're basically delegating all your capacity planning needs to your cloud provider. That way, if the initial setup doesn't have enough space, you can simply attach a bigger hard drive. Or if the program needs more RAM, you can just deploy the service in a virtual machine with more memory assigned. If you decide that moving to the cloud is a good way to go for your company, remember that you'll also need to plan for that. Migrating your services to run fully or even partially in the cloud requires work on your side. So you'll need to decide if and when to make the leap, to avoid your service having an outage because it ran out of resources. Throughout our course, we've called out several times that whenever we're faced with an issue, it's usually best to find a quick workaround so that those affected can get back to work as soon as possible. Say your database server crashed because it ran out of space. You can solve it quickly by adding an extra hard drive and starting the service back up. But remember, our work doesn't finish there. Once the affected users are happily doing their job, we need to look for a long-term solution that will prevent the problem from happening again in the future. In the database server scenario, that would be detecting that the disk is running out of space before it happens. So how do we do that without a crystal ball? One key strategy is to make good use of monitoring. There's a lot to say about monitoring, so much that we could have a whole course on this subject. The short version of it is that you want the computers you care about to send their data to a centralized location that aggregates all this information. And then you want to be able to look at both the information yourself and trigger alerts when the values are not within acceptable range. When you first set up a monitoring system, you might not be sure what information to prioritize. So start with the basics: CPU, disk, memory, and network usage. As time passes and you have to deal with more incidents, you'll probably discover other metrics that you'd like to include in your monitoring system. For example, if you had to debug a problem related to a computer overheating, you'll want to include the temperature sensor's data in your monitoring system. You'll also want to include information related to the specific service running on the computer. If it's a web server, you'll want to know the ratio between successful web responses and errors. If it's a database server, you'll want to know how many queries that are being served over time. And whenever you have to deal with an incident that wasn't caught by the monitoring system, remember to set up new monitoring and alerting rules that will notify you about the problem if it ever happens again. An important capability of monitoring is to include the measurements taken along a period of time. That way, we can keep track of how we're using our resources and catch changes and tendencies early on to help us with planning. Having good monitoring will let us know early on if things are broken. But how do we make sure that the things we fix stay fixed? We've mentioned this already, but it's worth repeating. If you have to work around an issue in an application developed by someone else, it's important that you report a bug to the relevant developers. That way, those in charge of the code can take your case into account and make it work correctly in the future. If you don't do this, it's possible that the workaround you figured out for the current version is not sufficient for the next version, and you'll have to figure out a whole new workaround. When reporting a bug to someone else, remember all the best practices that we talked about earlier. Let them know what you were trying to achieve, what you did, what the expected result was, and what the actual result was. Include your reproduction case and workarounds for the issue. If you have access to the source code of the project, providing a patch that fixes the issue increases the chance of that code getting fixed. On the flip side, if you have to work around an issue in the software that you own, make sure that you write a test that catches the problem. That way, you can be sure that you won't ever make a change to the code that will trigger that same issue again. And even if you're not in charge of the development of the software, you can still run automatic tests whenever there's a new version, just to check if it still works as expected. So make sure you perform these tests whenever a new version of the application comes around. Finally, regardless of whether the bug came from software that you wrote or someone else wrote, make sure that you document the key pieces of what you did, how you diagnosed the issue, and how you squashed it. That way, if the issue happens again, you, or whoever else needs to deal with it, will be able to quickly apply the solution instead of spending valuable time investigating.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.